Hi, I'm Mr. Evans, and today we're going to combine our previous two videos of potential and kinetic energy to talk about transfer of energy. And so hopefully you're aware of the law of conservation of energy, which basically says energy cannot be created or destroyed. It can only change forms, or it can only transfer. And so the total energy in a system, well, if it's a closed system, is always the same amount. So if you had 100 joules of energy, it can literally go through a million changes and you will have 100 joules of energy in some form. And so real quick before we do any actual math problems, and this is definitely where it's going to start getting trickier, is let's talk about a couple examples. So we're going to focus on roller coasters a lot in this class, and the transfer of energy from gravitational potential to kinetic and back. And so for the sake of doing a couple different things, we can talk about other forms of transfer of energy. So for example, let's do our car driving again, and I'll try to draw it a little bit better, and then I won't, and it's fine. So here's my car. I think that's better than last time. And it undergoes a transfer of energy in order to move, and its transfer of energy is from chemical potential energy to kinetic energy. So still, it's a type of potential. You can also picture, an elastic rubber band, and so as it sits there, not being stretched, it doesn't have much potential energy. However, you can stretch it out, right? And that gives it elastic potential energy. However, that energy didn't come from anywhere. You had to transfer it from your body to the elastic rubber band. And so in our class, we're going to focus on roller coasters. And so when the cart is up here, it has a lot of potential energy. And as it goes down the roller coaster, it loses potential energy, which becomes kinetic energy. And then as it goes back up the hill, the kinetic energy transfers back to potential energy. And at this hill, it actually has both, right? It has some potential, but it's also still moving, so it has some kinetic energy. And so what's cool is moving forward, we're going to be able to actually solve for exactly how much energy it has, both kinetic and potential. Okay, and I've tried to very crudely, in our bottom right hand corner now, draw a little toy roller coaster. And so we're going to work on actual real roller coasters in class with a lot more mass. But for the sake of keeping somewhat small and manageable numbers today, we are going to use smaller numbers to save some room. And so what I want to know is our cart is currently at the top of the hill, and we're going to assume it's not moving yet. And so I want to know how fast will it be moving when it gets to the bottom of the hill. So what will its velocity be when it reaches the bottom of the hill? And we're assuming that the bottom of the hill is on the ground. And so it's currently half a meter off the ground, and it's going to go all the way to the ground. And we have a 10 kilogram cart. So you might initially be thinking, well, I need velocity. The only equation that has velocity in it is kinetic energy. Let's solve using the kinetic energy equation. And you can write it out. You'll write out kinetic energy equals 1/2 mv squared, and you'll hopefully quickly realize you do not know velocity, you do not know kinetic energy. And so that is not going to work. And so let's use our potential energy equation and see what happens. And we have potential energy equals mass times gravity times height. And if we look over at our example here, we have mass and we have height. And so we can actually solve for this. And so let's solve for how much potential energy our cart has. So it has a potential energy that has 10 kilograms of mass, 9.81 meters per second squared for gravity, and 0.5 for the height. As usual, we'll just multiply that across, and so we have a potential energy of 49.05 joules. Perfect. And so what I'm saying is at the top of the hill, my cart has 49.05 joules of potential energy. And so as it goes down the bottom of the hill, we're going to assume it hasn't lost any energy. Energy cannot be created or destroyed. I haven't told you any of it is gone. And so we're going to assume at the bottom of the hill, it will still have 49.05 joules of energy. The difference is that energy is now kinetic energy, right? It went from being on top of a hill to moving. And so now we know, oh, we can plug that number in as kinetic energy. So now let's try our kinetic energy equation. Equals 1/2 mv squared. We know mass and we know kinetic energy, so now we can use it. We have 49.05 equals 1/2. The cart still weighs 10, right? It didn't magically change size. V squared. Now again, you want to save that exponent for last in this case, so we're going to do 49.05 equals 5v squared. And then I'm going to transfer the 5 over to the other side by dividing. And so that's going to get me 9.81 equals v squared. And our last step is to square root that answer. And so we get a final answer of 3.13 meters per second is velocity. And so what I'm telling you, and what I was able to solve for, is at the bottom of the hill, assuming we haven't lost energy, our cart will be moving at 3.13 meters per second. Now that's not realistic. It is going to lose energy, but I've told you that you can assume it's not. We will actually in the future do equations where it does lose energy due to typically heat and friction, but that will be in a later video, and definitely once we feel like we have mastered this. So I'm going to hopefully somewhat quickly go through another example, and essentially what I want to do is just the opposite. And so I want to say this cart is at the bottom of the hill and is going to get shot up a ramp. And so we have our cart, that last line, and we're going to say our cart weighs, let's just say it still weighs 10 kilograms. And let's say it gets shot at 7 meters a second. And so I want to know its maximum height. And so again, now we're doing the same thing, except for we're going from a ton of kinetic energy up a hill to potential energy. And so since we're starting with kinetic energy, we're going to start with the kinetic energy equation. So we have kinetic energy equals 1/2 mv squared. We plug in our knowns, 1/2, 10, 7 squared. We remember that the exponent only applies to the 7. So we get kinetic energy equals 5 times 49. If you're confused, 5 is just 1/2 times 10. So I just did these two multiplied together and then solved for this part. And so finally we end up with 5 times 49. And so we have a kinetic energy of 245 joules. Now again, we're going to assume none of it was lost as it goes up the hill. And so all that kinetic energy becomes potential energy. If we're looking for maximum height, that would be the moment it stops on the ramp. And so all of it becomes potential energy, and so now we plug it into our potential energy equation. So we have 245 joules of potential energy equals a mass of 10, 9.81 times for gravity, and we're looking for height. So I'm going to do 245 equals, we can do 10 times 9.81, which is 98.1, times height. And then all you have to do at that point is divide over. And so you divide by 98.1, cancel out, 98.1. And so our final height, sorry I'm kind of running out of room, is 2.5 meters. And so what I'm saying is if we have that size cart, we shoot it at 7 meters per second up a frictionless ramp, it will reach a height of 2.5 meters. So we'll do more questions like this in class, and that is how to solve for transfer of energy. Our next two videos will cover loss of energy, so you can't actually destroy energy, but it does get lost through heat and friction, and so that will affect our cart. And then our final video will be incomplete transfer of energy, which would be, well, what if it only goes halfway up the ramp?